Hey guys, Steven here. If you're a pro at wiring control panels or troubleshooting machines and systems in your plant, but you have no clue what to do when it comes to programming a PLC with ladder logic from scratch, this video is for you. I put together a structured process for you if you want to learn ladder logic, and I've got it in an order that actually makes sense. I programmed PLCs hands-on for over 10 years. I started my PLC training back in 2016, and since then I've helped hundreds of electricians, technicians, and engineers go from never opening the software to getting hired into actual controls roles. This is ladder logic start to finish, what it is and why plants still run on it, the one idea everything will build on, every instruction you'll actually use, the traps that break beginners' programs, and then we'll read a real program together rung by rung. By the end of this, you'll have the whole language in one place and a great starting point for understanding ladder logic. Okay, so let's talk about what ladder logic is and why it's still running in plants in North America in 2026. Ladder logic was built to look like circuit diagrams, relay circuit, control circuit diagrams. They have different names, sometimes control schematics, and it was meant to show how that logic works, where contacts are either closed or open, and basically whether the circuit is true or not, and the different paths that the current can go through a circuit to turn on an output or turn on a relay coil. The reason was because the engineers, the technicians running the plants, designing automation for plants, that's what they were familiar with when PLCs were just invented. The inventors wanted those engineers and techs to be able to transfer that knowledge to programming a PLC. Power flows in from the left and goes through any contacts or instructions and goes to the right towards the coil. You can think of it as your DC power on the left, this is my left anyway, traveling through to the right side of the rung. And when it reaches that end, it's going to turn on that coil or that output instruction. The overwhelming majority of plants in the US still heavily use ladder logic in their PLCs. Obviously, there are other programming languages, structured text, function block, sequential function chart, and then you'll even hear people talking about Python or using AI to program PLCs. But what is actually running in plants right now is ladder logic for the most part in North America. That's why you want to learn ladder logic still in 2026, because it's the skill that employers are actually hiring for. Now, this whole guide is based on ladder logic in Studio 5000, which is the Rockwell automation software that is used to program control logics and compact logics PLCs. And the reason I chose that one is because it's the most commonly used PLC in North America. There are other important brands up there, Siemens and Modicon and Automation Direct, but Allen Bradley still has the market share in the US in terms of plants running their PLCs. This is the skill that most employers are hiring for, the ladder logic and the Studio 5000 knowledge with control logics, compact logics. So that's what we're going to focus on in this video. Before we write any ladder logic rungs, you need to understand this about the PLC, and that is the scan cycle in a PLC. The PLC doesn't read your logic like reading a page once and then being done. It runs the whole thing in a loop, over and over and over, very, very quickly. The traditional PLC cycle, it reads the inputs to the PLC, takes a snapshot of what state they're in. This one's on, this one's off, this one's on, etc. Then it runs the code based on the status of those inputs, and then it processes the outputs, turns them on, turns them off, whatever needs to be done. Now, with control logics and compact logics, it's a little more complicated than that. You can actually run logic at scheduled times. It's not always necessarily running after all the inputs are scanned, etc. So it's a little more complex, but this is the basic idea. It's reading the inputs, it's processing your logic, and then it's turning on the outputs. As you get into more advanced programs, you do need to understand intricacies of control logics and compact logics asynchronous scan cycle. But the main thing you want to understand is that the way the logic is scanned when it is reading through a routine is just how we would read a page. You start at the top, you read from left to right. one line, then you go down to the next rung, read from left to right, so on and so forth. Don't assume that everything happens at once, which in the physical circuit world, everything does happen at once. If power is applied at this point and this point and this point, all those circuits are going to act simultaneously. Whereas in the PLC, you're going to run rung 2 before you run rung 40, for example. The order of your rungs does matter. It usually doesn't make a huge difference depending on your program and how important the speed and the process is. Generally, it's best to consider the steps of the process and write the first step in the process on a higher rung and a further step on the process on a lower rung. And a side note here, you just want to be careful about having an output instruction in multiple places in one ladder or even multiple routines within a program. That's usually a very bad idea, and we'll come back to that more later. So let's talk about your first rung and the instructions that started it all, the contacts, the coils. These are what I call the relay type instructions. These are what you'll see that look similar to a control schematic in a real relay circuit. First, we've got the XIC, or examine if closed. This looks like a normally open contact in a relay circuit, meaning at its resting state, it's going to be open, so you're checking to see if it's closed. Examine if it's closed, then we're going to pass current through. Now, with the examine if open, or XIO, this is supposed to look like a normally closed contact, which normally allows power to flow through. We are checking to see if it's open. The way this one works is in its resting state, it's actually closed, allowing power to flow through. And when it turns on, opens up, allowing power to not flow through. Examine if open corresponds to a normally closed contact. Confusing, I know, right? Open, closed, blah, blah, blah. But you just need to understand that concept of closed circuit versus the open circuit. You're trying to check and see if it's closed or open. The output energize, or OTE, is like the relay coil that lives on the right side of the rung. And basically it's checking to see if power goes all the way through the rung to reach that coil, and then it's going to turn on. Generally, that's going to be tied to physical output, maybe a motor or a light or some sort of solenoid. It's usually tied to something that you're turning on and off in the plant. Okay, and then we have series and parallel. To have both contacts would need to be true for the power to flow through. In parallel, if you've got two contacts in parallel, either or needs to be true for the output to turn on. Let's build a couple things here real quick. So if we've got an XIC here, and we call this input 1, we'll just create that tag there. Let's say we've got an OTE here called output 1. Now, this is not running in an emulator or a real PLC, but if we were to toggle this on, it would toggle this output on, right? Because we've got a path from left all the way to the right here when this is on. And then when this is off, it would directly turn off this. Okay, so that's the most basic type of routine you could create. And then if you were to make a parallel here, parallel rung, and let's say we had a separate input 2 here. Now either input 1 or input 2 can turn on output 1, because either one can provide a path from the DC positive to allow power to flow through all the way to the coil down to DC negative. Okay, if you wanted it to be where both inputs had to be on, you would put them in series. So that would mean input 1 and 2 both have to be on for power to flow from the left to the right to the coil. And as we talked about, the XIO would work similarly, but a little different, where if we had an XIC and an XIO, the XIC would need to be on and this input would need to be off. So you can see the value says 0 there, meaning the underlying tag is 0, but it's showing green, meaning the instruction itself is true. It's allowing power to flow through. The underlying tag of input 1, the value is 1. So that matches, the tag value matches the instruction value, whereas with the XIO, it's the opposite. If the value is 0, then the tag instruction looks like it's on. And vice versa, if we were to toggle this off, now you can see the underlying tag shows 1, but the instruction shows off. Now again, if these were both allowing power to flow through, that would toggle this on. Again, I'm not running this logic in a PLC brain, so I'm just toggling these on manually. Next, let's talk about the classic seal-in circuit, sometimes called a motor start-stop circuit, or what I like to call it is a make, seal, break circuit. Basically, the functionality is you've got a momentary push button to start it and a momentary push button to stop it. When you push that start button, it starts the motor and it stays running even when you let your hand off. And then when you're ready to stop it, you push the stop button and it turns off. Obviously, if the motor only ran while you were pushing the start button, that wouldn't be very useful. We want it to seal in until we turn it off with the stop button. You're making the circuit when you're pushing it in, and then you create logic to seal it in, and then when you push stop, you break that seal. Let's look at what that looks like. Here we've got a start push button and a motor start output here, and we need a way to seal this in and to turn it off. Let's say we have a stop push button here, and this could be an XIC or XIO depending on how the input is wired to the PLC. That's a topic for another video, but we'll just assume it's like that, and then we will seal this in. The way you seal this in is by using the same tag that you're using for the output. In other words, when this output goes true, you use itself to seal it in. We put an instruction here, motor 1 start. This will initially go true, pass the current through here, turn this on, which will latch this in, and that will basically keep itself latched in with this contact. And this is exactly the type of control circuits that you'll see with physical relay circuits in the real world. And then the stop push button is there when you want to break that sealed circuit. So I went ahead and downloaded this program to an emulator controller so we could test it out. So I'm going to toggle on this start push button, which is the same as if we had a push button physically pushed it. It would turn on that input to the PLC and this will go green. So we can simulate that by just right clicking on the bit and clicking toggle bit. Now you can see this turned green, the motor 1 start, and anytime this output goes true, any other places in the program where that same tag is used, it's also going to go true. So you can see it went true here, just like we wanted. So now when we release that push button, in this case we're going to toggle it off, you can see it stays sealed in. So we made the circuit, now it's sealed itself in. The next step is when we want to turn it off, we need to break that circuit. So that's what the stop push button does here. So if we were to push that, or in this case, we'll simulate that by toggling the bit, and we release it, the circuit is broken. It remains off until we repeat the cycle by turning the start push button on. Release the button, stays sealed in. Again, when we want to turn it off, push the stop button, it breaks the seal. So that is your classic motor start stop seal in circuit. Now there's another way you can do this with an output latch and an output unlatch instruction. That's very simple. You'd need to use 2 rungs instead of 1. So that's another way to do it. We'll save that for another time. On and off programs are kind of the basics of what you'll see in a PLC program, but real programs have delays and counting involved as well. So let's look at timers and counters. There's 3 different timers available in Studio 5000. There's the TON or timer on delay. There's the timer off delay or TOF, and the retentive timer on delay. For me, I always found the timer on delay to be the most intuitive. Some people prefer the TOF, and some applications lend themselves more to one or the other. But the way these work is if you have a TON, this is kind of the basic one. Basically, we're saying we'll create a tag here, call it timer 1, and then you set a preset, which means the amount of time you want the timer to time. So let's say we want it to time for 10 seconds. They use milliseconds here, so you would need to put in 10,000 milliseconds if you wanted it to time for approximately 10 seconds. And then whenever this rung was true, which at this point it would always be true, let's put something in front of it like motor 1 start. When this output turns on, that's when we start the timer. Then this timer will time for 10 seconds and then it will go done, as they call it. So the done bit will activate. We'll just do a quick demonstration of that. Timer 1 done bit will be on this rung, and then I'm going to put, it's called a no operation at the end because we don't want this to do anything. We just want to kind of watch the status of these bits in the timers. There's the done bit, there is the TT bit, or timer timing bit, which turns on while the timer is timing. And then there's the EN bit, which just tells us if the rung in condition to the timer is true or not. So what we can do is go ahead and download this to the emulator. I've got online here with the emulate controller, and we've got this timer on delay that's being controlled by the motor 1 start bit, and we're going to see how these timer bits respond when the timer's running. So this is the done bit that's supposed to turn on when the timer on delay, and then there's the timer timing bit that's supposed to turn on while it's timing, and then this one's just always on when the input to the timer's on. If we toggle this on, and we'll release this, you can see the timer's timing up. We're at 6 seconds, almost to 10, and when it gets to 10, the done bit turns on and the timer timing bit turns off. The timer off delay works different than that. The done bit actually starts out on, and then it turns off after the delay of the timer starts. And starting the timer is different as well. You want to go from true to false to start the timer off delay. And then the retentive timer allows you to retain a certain amount of time even if you stop the input. So for example, if it's a 30-second timer, you turn on the input to the timer, it times up to say 17 seconds, and then you turn off the input. It holds that 17 seconds, and then when you turn on the input to the timer again, it's going to start timing from 17 up to 30, assuming it stays on that long. So it remembers where it left off. And then with counters, we got our count up counter and our count down counter. The classic example of how you would use this in the real world is a parking garage, where you've got an entrance to the parking garage and an exit from the parking garage, and you want to count how many cars have come in and how many cars have gone out, so you can show a number to the drivers coming in to show them how many spots are available, or if there's no spots available. There's a lot to ladder logic, and reading about it and writing it yourself are two very different things. Closing that gap is the whole reason the Confident PLC Programmer Accelerated exists. In the program, you get access to Studio 5000 to build every bit of this logic on your own machine. You get the full course path through PLCs, HMIs, and drives, and a coach who will look at your screen when a rung in your program doesn't do what you expect. If you're serious about doing this for a living, the link's below. Either way, let's keep going. The next part is where your logic starts making decisions. Let's move from talking about on, off, and timers and counters to ranges of numbers, working with analog inputs and outputs. That's where you're going to be looking at using instructions like comparison instructions and math instructions. A comparison instruction basically asks a question to compare two values. So you can compare anything you want. Say you have an analog input from a tank that's telling you what level the tank is at. You could compare that tank value to a fixed value, say 50. When the tank value reaches 50, then do this, for example. Or when it's less than 50, do this. The compare instructions, there's several of them. You can do kind of a generic compare and write your own comparison formulas. Or you can use these preset instructions like a limit instruction, masked equal. These are kind of a little more advanced, but then you get your classic equal. So you're comparing to see if one value is equal to another value, simple enough. Or if one value is less than another value, then it's true, and it's going to allow you to do the next part of the rung. Greater than, less than or equal, greater than or equal. Examples of how you might use this in the real world, I can take experience from the switchgear company I worked for. We would be controlling generators, and sometimes you would have multiple generators, and you would want to only run one generator if you didn't need to run the other ones. You had two generators, and you only wanted to run one unless the load on that generator got above 60%. So you could use a comparison instruction to compare that load on the generator that's coming in through an analog input, for example. Obviously, there's 1,000 different ways you can use these comparison instructions, but they're very valuable. And think about it like it's true-false equation, where you're comparing more than just one and zeros. You're looking at a range of values, but you still need to make that comparison give you a true or false output. Next, you've got the math instructions, where you're actually doing mathematical operations on values. You can add a value, two values together, and get a combined output, for example. Like you could take your analog output that displays a value on an analog gauge on a control panel, and you could add a value to it if you wanted it to show a little bit higher, and you could basically use this as a scaling function. Or you could have some logic here that basically adds a little bit to the set point every time you push a button, for example. Say you've got a set point for a motor speed, and you want every time you push that button to add 5 RPMs to the motor speed set point. You could use a input here and maybe a one-shot instruction, which we'll talk about later. And then of course there's the other math instructions where you could subtract a value from another value, multiply, divide. These are great for manual scaling of an analog input. If you're getting an analog input in kind of a raw value that's kind of ugly and you want to convert it to, say, gallons for a tank or RPM for the speed of a generator or a motor, then you can use these math instructions to convert it from the ugly raw value to the actual engineering units you want to use, that RPM or gallons or whatever it is. And then you've got a move instruction, which simply allows you to move one value into another tag. You can move the value of one tag into the value of another tag, or you can move a hard-coded value like 35 or 34 into a tag like motor speed set point. And you could set up the rung so that whenever it's true, whenever this bit is true, motor set point start, that it's going to put 34 into that set point. If we were to actually download these edits, we can actually test this. Right now you can see motor speed set point is 0. If we turn this on, it now went to 34. It moved 34 into the motor speed set point. That's how you would use a move instructions. Very useful. These are the most important instructions: the relay type instructions, the counters, the timers, the comparison instructions, the math instructions, and the move instructions. Honestly, these cover about 90% of what you're going to do in PLC programming. There's a lot more that you can learn and eventually you'll want to learn, but these are the ones that are going to give you your biggest bang for your buck. Rather than going and trying to learn the other instructions, focus on these until you're really comfortable with them, and then you can always venture into the other ones later. Now, one other quick instruction I want to talk about is the one shot. The one shot is a unique instruction that only runs once per scan cycle depending on the input status. So what that means is, rather than explaining it too in depth, I'm going to show it because it's kind of hard to explain without showing it. Basically, this instruction will be true for one shot, thus the name. In other words, if we toggle off this bit, this rung condition is false, so the one shot's going to be false. When we turn this to true, the one shot will be true for one scan cycle. So remember we talked about scan cycle earlier. It goes through the program and it loops through that over and over and over. But the one shot, what it does is it only allows that to be true for one shot until the input condition before it goes false and back to true. For example, let's set this value back to 0, and we're going to toggle this bit on, and you can see it moved 34 into the motor speed set point. But now what I'm going to do is I'm going to force this value back to 0, and look, it stays at 0. So even though this is true and this is showing true, it's no longer moving that 34 in here because this only ran for one shot. So if we wanted it to run again, we'd have to reset what was before it, toggle it back on, and now it allowed the logic to run one more time, moved 34 into the set point. Again, that's very valuable in certain situations where you want to only pass something through one time and then wait for another operation before you actually allow that output or that move instruction to go true. So here's a tip that you want to avoid. You never want to have another rung that has the same OTE or the same tag referenced with an OTE. So you would never want to have another rung here that says, say, timer 1 done. Say you're trying to turn off the motor start when the timer's done. This is going to be a conflict. This is going to be controlling it, and this is going to be controlling the same output, and they're going to be conflicting and battling back and forth. It's not pretty. You can cause big problems by doing that. So never use a tag more than once as an output. Now, if you're using the latching output and unlatching output, you can use one of each, and that's fine. One latching, one unlatching, but you don't want two latching, two unlatching, etc., and you definitely don't want 2 OTEs. One other thing I want to talk about is how you name your tags. There were different theories and philosophies about how you should name your tags, and I encourage you to kind of explore the different options that people present. I would say a safe default for how to name your tags is nice and clear language. You can see here I put motor _1 _ start, and then we have start _ PB for push button, if that's commonly understood at your company. That PB stands for push button, or motor _ set point _ start. You can't use spaces in your tag name, so you have to use underscore if you want to kind of separate words, but then that is kind of a good default way to name your tags. And of course, if you have multiple motors, you want to use the same exact syntax for each motor start, each motor stop, or whatever it is. Motor 1, motor 2, motor 3, etc. Also, in terms of organizing your program, it's usually a good idea to have multiple routines for multiple parts of a process or a machine. If you have an alarm ladder, that's something you want to have separate from your main control routine. In my case, when we were programming for switchgear in data centers and power plants, we would have separate routines for controlling each breaker in the system, a routine for a generator, controlling the generator on and off, a routine for loading up the generator. You need to know your system and divide it up kind of in a natural way for how you control your machine or process. Next is comments. This is just as much for somebody else that needs to read your code as it is for yourself, because to be honest, in 6 months, you're not going to remember why you did certain things in your program. So you want to leave comments for yourself and for others to remember why this is the way it is and what it does. Motor, start, stop, logic for motor 1 is kind of a clear basic comment. Obviously, this is simple logic. If it's more complex, you need to give a little more explanation of what it's doing. Push button for setting motor speed to 34 RPMs. Okay, something like that. Again, something is always better than nothing, so it doesn't have to be a perfect explanation, but the goal is that you want to help yourself and others figure out what this logic is intended to do. So you want clean tags, you want commented rungs, and you want well-organized routines, programs, and tasks in your program. Now I want to go through a ladder logic example that we use for some of our training, and we're just going to go rung by rung and see what this does, how it works. So if we start with rung 0, this is controlling a main conveyor motor. So I always look at the output first to see what we're even achieving here. So this is some sort of motor we're turning on and off, and you can see this is a familiar look to what we looked at earlier with the seal in type logic, where this is sealing in and these are breaking the circuit. This is a start push button that's on the HMI, so when that goes true, and if the HMI stop push button is not pressed, then it's going to toggle on this. I'm just doing it manually here to show you, but that would seal it in even when you release that push button. Seal it in so your main conveyor motor is going. Simple enough. And then either of these conditions here, if there's 50 barrels in the loading area, which we'll talk about, or if the stop push button is pressed, both of those would interrupt that conveyor motor. Here we've got a counting instruction, basically resetting these count up and count down. So we'll actually look at those before we look at this one, but this one says barrel enters loading area. So there's an input here that is a discrete input coming in on this input module, it looks like, slot 2. And when it turns on, we count up and say there's a barrel in the loading area. And when this input turns on, we count down and say there's one less barrel in the loading area. Counting barrels coming in and barrels going out to give a total value of how many barrels are currently in the loading area. Now we have a greater than or equal instruction that says when there's 25 or more barrels in the loading area, we're going to turn on this indicator that says there's 25 barrels in the loading area, and then this is going to be used on the HMI to trigger a banner or a notification. And it looks like down here, I'm skipping ahead a little bit, but if barrels 25 in loading area is on, then we turn on a warning light, and that's what's showing up on the HMI. And then we've got this other greater than or equal instruction that says if there's 50 or more barrels in the loading area, we'll turn on this one, which actually turns on the barrels 50 light, and it also turns off the main conveyor conveyor motor when this turns on. Okay, so that's an example of a basic PLC program with counters and comparison instructions and relay instructions line by line. That's how you start to read ladder logic. Now you've seen the fundamentals of how ladder logic works, and obviously this is just the beginning. You need to get reps in with real software, building programs, testing them out, and that's how you build real confidence. And when you have a portfolio of programs and projects that you've built that you can show to an employer, that's when you have something that can help take your career to the next level. And then once you have that, you combine it with HMI skills and connecting drives to the PLCs, and you've got something that's valuable to employers, what they're looking for, controls people that know PLCs, HMIs, and drives. That's the whole language: contacts, coils, timers, seal-in logic, comparisons, one-shots, and how to write your logic so that the next tech or engineer can actually read your program. Reading it is one thing, but the first time you build a rung yourself and watch it go true in the logic, it stops just being theory. Your next step is this video I made a few years ago that's more of a tutorial style video on ladder logic that reinforces what we talked about here. It should be on the screen now, so check it out. And of course, if you have access to the Studio 5000 software, open it up and build the logic right alongside me in the video. We'll see you next time.